And one more example I just specified, dear friends. If you have 3 yes and 3 no, in such a case, which one do you choose? Here 3 yes and here it is 3 no. We would just say as like a cat on the wall. Both the sides, here it is both are equal. 3 yes and 3 no. Even though we don't have any such majority thing. Okay, in such a case, let I just calculate the if this is our F3. Okay, if this is our F3 minus among 6 sample, okay, I have 3 positive, so log 2 of 3 by 6, and among 6 I have 3 negative, and again 3 by 6, which it just leads to 1. And of course it was most impure entropy. So of course you all know this entropy, yes, we have 0.94, and totally it is 14 samples, and among 14 samples we have 5 for sunny and 4 for overcast and 5 for rain. And here we have to apply this value, that is the value of subset. We have to apply, and we have to calculate the information gain of outlook, and we just got 0.2464. And yes, dear friends, with the highest information gain, kindly just see, yes, outlook, if it is sunny towards the humidity, we can easily, I have already specified this F3, which it just had 3 yes and 3 no. And of course, you remember the exact entropy here we just reached is 1. Yes, and we have also specified it as like a worst split or a not a good entropy. Now let me just take the same thing here and apply towards this equation, and see here, dear friends, let I have the same 1 minus summation of positive probability and negative probability. Okay, so here Pi, of course I have 2 splits, so P1 the whole square, that is the positive the whole square, and P negative the whole square, that is 1 minus 3 by 6 the whole square. Among 6 samples we have 3 yes, and among 6 samples I have 3 no, and with this one by 0.25 plus 0.25, which it just leaves 0.5. Now, one thing just to see here, dear friends. When previously it was just specified as like 1 and as a word split, now it is nearing to 0 something purity. Dear friends, in regression tree, instead of calculating entropy, we look at how much variance or error is reduced after a split. Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, today in this session, we are going to break down one of the most foundational yet fascinating algorithm. Yes, it's decision tree. Dear friends, you might be thinking, how do machine make decision? How do they know whether to approve a loan or not, or classify an email as a spam or not, or even recommend your next favorite series? Okay, in this session, we are going to explore the core mathematics and intuition behind decision tree and build our understanding from the ground up. Yes, first we are going to discuss on entropy. Second, then we walk through to the information gain. And finally explore an equal important alternative called Gini impurities or Gini index. Different. A decision tree is a supervised learning algorithm, meaning it requires labeled data to train. It can be used for both classification and regression model. Of course, for this, it is also just a specified classification and regression tree. So, which is specified as like a cart. Okay. So, but it's particularly famous for its classification task. Dear friends, think of it like this. Every time we make a decision in life, like choosing whether to carry an umbrella, we consider an few conditions, whether it is cloudy, or what's the forecast, did it rain yesterday. So we subconsciously go through a series of check, and based on the answer we arrive at a final decision. Dear friends, so that's essentially what a decision tree does. It's like a flowchart like structure. Each internal node tests a feature or a condition. And here each branch corresponds to outcome of that condition, whether it is yes or no towards this feature. And when on just going towards the leaf node, of course, it represents the class label or decision. Dear friends, it starts from the root node and recursively splits the data set based on the feature that gives the most informative decision boundary. But how do we mathematically determine where to split? What's a good feature? Which split brings the best purity? So to answer this, first we need to understand entropy, and let me just get depth into the information gain. Then we decide how far this process is going on. Okay, towards this, let I just give you the each step of our process. First of all, of course, the decision tree, whether it is for classification or regression. Gather all the data and with the functionality, just calculate the entropy. And next one, so that entropy we have to calculate for each and every feature, because we have to select which feature to be the root node. So yes, we have to calculate for each feature. And next, of course, we have to apply information gain. And here also we have to apply it for every multifunctionalities of the nodes. And the next, here it is for recursive. That is how far this recursive has to be done or to be repeated, or how far the split has to be happened. All these things we have to stop here. So let me just go for the first step. Of course, we are here in the first step. So we are now going on towards the classification task. Okay, so let's begin with the basic. Dear friends, of course, you know that the decision tree is a structure where we split our data set based on towards the feature or attributes. And at the end of these branches, we have a leaf node, which are basically our final class label. And here it would be as like whether it is yes or towards no. Okay, fine. So now let me suppose we have a feature of F1, F2 and F3. And we have a target output that it's in binary. So meaning it is either yes or no. Now, to build this tree, we are going to have an algorithm. Of course, it is ID3 that guides us. And the very first step in ID3 is selecting the right attribute to split on. But how do we decide which feature to choose at the top of the tree, whether it is F1 or F2 or F3? Of course, this is where entropy works in. Dear friends, entropy, here I just let you know again, entropy is used to measure the purity of split. Okay. Now, when you split the data set using a feature, how cleanly does it separate the class? There we have to go to our discussion. Okay, so before split, Let me just say here. Okay, so let I just take an example. Let me just have 9 yes and 5 no. So totally we have a 14 samples. And before the split we have like this, and of course that's our output class distribution. Now we try to have here as F2, and here we have this F2 as like 3 yes and 2 no, or another branch we can have 6 yes and 3 no. So somewhat like that. But here it is not perfectly pure because each branch has a mix of both the classes. But what if we go a step deeper? Dear friends, kindly just observe here when it just comes to an end. How long we have to go towards the split, yes or no, or yes or no, like this. So one thing, if we have a pure node, when it achieves, for an example, if you are having a subset of 3 yes and 0 no. Perfect. That is pure because we are deciding yes, it is 3 yes. There is no no. 3 yes, only yes. Or if we have another subset as like 0 yes and 2 no. Again, it is a pure. So, yes, dear friends, here to achieve these leaf node, we have to make our split, and till reaching this leaf node, we have to make the split. So, and to know if a split is leading us closer to purity, yes, we are going to calculate our entropy. So, mathematically, how this entropy has to be specified is, kindly just observe. Entropy is minus positive probability log 2 of positive probability and minus negative probability log 2 of negative probability. Here, let we just have, as of all I have previously I just specified, let we have this F2 now. Okay, so in such a case, here I just have this F2. Okay, so here entropy of F2, okay, entropy of F2 I just applied here. We have 3 yes and 2 no. Okay, so totally we have 5 samples. So among 5 samples I have 3 positive, okay, and log 2 of 3 by 5. And among 5 samples I have 2 negative into log 2 of 2 by 5. And observe here I just get entropy of 0.78. And when I just go towards this one, F1, okay, so here I just calculate F1. So it's among exactly. So here it is 9 yes and 5 no. So totally it is 14 samples. Among that 14 samples, I have 9 yes. So log 2 of 9 by 14. And among 14, I have 5 no. So log 2 5 by 14. So which it just leads 0.94. Kindly just observe whether it is nearing to 0 or nearing to 1. Both are nearing to 1. And if a entropy that is closer to 0, yes, of course you can just say a purity node. But here both the things are not related towards purity or not closer towards the purity. So for an example, if I just specify, so for an example, let me just have a node F3. It has 4 yes and 0 no. In such a case, only yes. So 4 yes, there is no no. So in such a case, here it would be an entropy of 0, which it leads to purity. And one more example I just specified, dear friends. If you have 3 yes and 3 no, in such a case, which one do you choose? Here 3 yes and here it is 3 no. We would just say as like a cat on the wall. Both the sides, here it is, both are equal. 3 yes and 3 no. Even though we don't have any such majority thing. Okay, in such a case, let I just calculate the, if this is our F3, okay, if this is our F3 minus among 6 sample, okay, I have 3 positive, so log 2 of 3 by 6, and among 6 I have 3 negative, and again 3 by 6, which it just leads to 1. And of course, it was most impure entropy. So, if the split, even if it is nearing to 0, we can just say it is purity. But here it is exactly 1, which is an impurity. Dear friends, how far you have to decide which future? Now kindly just see here, which is the minimum one towards entropy, 0.78. 0.94, and here it is 1. Of course, minimum it is 0.78, but even though it is nearing or closer to 1. So, now after calculating this entropy, we have to choose the feature that reduce entropy the most, because that gives you more information. So, here to reduce the entropy or to further calculate, we need, of course, we need information gain. Dear friends, we here discuss only one node, but in real tree we have multiple levels of split. So we need to have an information gain to summarize the overall reduction in entropy. Okay, so let me just have that. And in such a case, whenever we are just going towards entropy, kindly observe, dear friends, here there is a calculation, that is, I just want to make one particular set of entropy. So let I just have A. If my future A is my attribute, if I just want to go towards that future, I have to calculate. So H of S, that is entropy before the split, minus summation of, here I have to evaluate it for this A node. In such a case, I get a value of this, that is a subset of data for which future A has a value of V. And this is what the subset functionality, and let I have HSV. It is entropy of subset. I just give you with an example, just for an example. So kindly just see here, this is what information gain. Before going on to information gain, let I just give you again this functionality. So this tree. So here 9s and 5 no. Okay, and this is for F2, which I just have 6s and 2 no. And here let we have F3, this is 3s and 3 no. Let we have this sample. Okay, so before the split, I have this one. And you already know entropy of 9s and 5 no. Let I just scroll above and observe it. Okay, here we have. Okay, so this is what for 9 yes and 5 no, and with 14 samples. Okay, so with that, I have the calculation of 0.91. Okay, now taking it towards the functionality, just observe, dear friends, here I have to make a summation of all the subsets. So what are all the subsets? Of course, I have two subsets, that is F2 and F3. And with this 9s and 5 no, I have 14 samples. And among 14 samples, here I'm just giving 8 for this, and here I'm just giving 6 for this. So kindly just observe. So minus among 14, 8, 1 probability, and here F2, entropy of F2. What is entropy of F2? So let I just have it. Entropy of F2, it is 0.78. Okay, so let I just have that 0.78, and another F3. and towards this F3, it is 6 among 14 and its entropy is 1. And kindly just observe, on calculating, I just get 0.049 as my value. Dear friends, here we repeat this for other futures also. Other futures how? F2 would be the top, and let me just have, this is F1 and F3. Calculate the entropy of F2 before the split, and then next for this. And again we have to make F3 as our root node and further F1 and F2. And this was specified as the step 4, which we just give recursive or splitting. So once we make the first split, we don't stop there. We look on to each child node and repeat the same process. We have to calculate the entropy, we have to calculate information gain and split further. And kindly just observe when this first splitting would just ends. Of course, if all the samples in the node belongs to a single class or entropy is equal to 0, in such a case, we stop our process. Or no more speeches or left to split, we can stop it. Or further, a maximum depth. Kindly just observe, a maximum depth if it is reached. How far? You just say if an user specified, yeah, this is the exact max depth is equal to 50 or max depth is equal to 100. Why means, of course, to prevent overfitting, the user can set the splitting depth or maximum depth to some value. Okay, so if that maximum depth is reached, yeah, we can stop our recursive. Or further, if a minimum number of samples per node is satisfied, minimum sample per node condition is satisfied. So eventually the tree stops growing and becomes a collection of this decision path. Each path ends in a leaf node that makes the final prediction. So alright, now that you have got a strong grip on what is entropy and information gain. Okay, so it is time to discuss about another popular metric which is used in decision tree, that is Gini impurity. Dear friends, if entropy comes from information gain, Gini impurities comes from the field of probability and statistics. Specifically from the Gini index used to measure inequality. Okay, what is actually Gini impurity? Dear friends, Gini impurity measure the likelihood of incorrect classification. A randomly chosen element. So if we randomly label it based on the distribution of a class in a subset. Okay, so here this is mathematically it is specified as like a Gini of a subset. If I just specify here, it is 1 minus summation of I is equal to 1 to n and pi the whole square. I have already specified this F3, which it just had 3 yes and 3 no. And of course, you remember the exact entropy here we just reached is 1. Yes, and we have also specified it as like a worst split or a not a good entropy. Now let me just take the same thing here and apply towards this equation. And see here, dear friends, let I have the same 1 minus summation of positive probability and negative probability. Okay, so here pi, of course I have two splits, so p1 the whole square, that is the positive the whole square, and p negative the whole square, that is 1 minus 3 by 6 the whole square. Among 6 samples we have 3 yes, and among 6 samples I have 3 no, and with this 1 by 0.25 plus 0.25, which it just leaves 0.5. Now, one thing just to see here, dear friends. When previously it was just specified as like 1 and as a word split, now it is nearing to 0 something purity or leading towards purity. Or we can just say, for an example, if we have previously what we just have, let we have this pure probability, and here it is our threshold of 0 to 1, which is just reached the worst split. But now which we just reached the entropy previously, and now it is reduced to 0.5, where we just reached by using Gini index. So this is what our Gini. So if all elements belong to one class, or even though here the Gini, if it is leads to 0, yes, it is perfectly pure. So before it is worst, now it is closer to 0. And we would have a confusion. Of course, we are having 0, so 1 entropy here. The same here, when on using Gini index, we just got 0.5. When to use which one? So kindly just observe one thing, dear friends, an important functionality. Of course, here for entropy, we just have a range as like 0 to log 2 of n functionality. But here in Gini index, it is 0 to 1. It is only 0 to 1. And towards the bias, yes, of course, dear friends, it is favors when you have a balanced split. There you can make use of entropy. And if you have a large number of classes, you can go for Gini index. And of course, when on comparative, of course, this entropy is slightly more complex. But why? Because it is using logarithmic functionality. And here, as it is not using the logarithmic, this Gini index is not using the logarithmic, it is a bit faster. Or we can just specify, yes, it has a shortest execution time. But here, kindly just observe when to use. Yes, according to usage, if you have a problem statement under ID3 or C4.5, kindly make use of entropy. Or if a problem statement that can be used both in classification and regression part, that is CART. Yes, of course, you can just go with Gini index. Okay, now let me take a data set and let me discuss about the entropy and information gain. Dear friends, we have 4 such features, that is outlook, temperature, humidity and wind. And we want to predict whether a person will play tennis, yes or no. Now we ask which feature should split on first, whether it is outlook or temperature or humidity or wind. Why is this important? Because the first split dramatically impacts the structure and performance of the entire tree. And kindly just observe, dear friend, a bad split early on may require many more branches later to compensate. So while a good split simplifies everything. And dear friends, we evaluate each features and calculate how much it helps reduce uncertainty and using a metric called information gain. And before information gain, yeah, we have to calculate the entropy and then we have to pass on towards it. Okay, now kindly just observe. So let's begin our decision tree construction by selecting the attribute that gives us the most information about our classification target. So first, let me have the outlook. Okay, and the first attribute, it has 3 values: sunny, overcast and rain. And dear friends, our goal is to evaluate how much is split the data based on outlook reduces the uncertainty or entropy in a data set. So to do that, we must calculate entropy of the whole data set. Entropy of the whole data set and entropy of each subset created by outlook and information gain, the amount by which the entropy is reduced. So first of all, let me just have the entropy of the whole data set. And towards the whole data set, kindly just observe, we have totally 14 samples. And among these 14 samples, kindly just observe, we have 9 yes and 5 no. Yes, 9 positive examples and 5 negative examples. We can just say or yes or no like this. Okay. So here we have calculated the entropy of this whole data set, which it just has 14 samples. And among these 14 samples, we have 5 no and 9 yes. Okay, and among this, of course, we have positive probability and negative probability. And kindly just observe, dear friends, we just got the calculation of entropy as 0.94. This is our baseline uncertainty. Any attribute that can reduce this entropy significantly, we will be strong enough for the root node. That is, this outlook would be strong enough to choose this as our root node. Okay, now let me have the subset of each everything. So here outlook, it just has a subset of sunny, overcast and rain. Kindly just observe only this sunny here. I'm just taking it, and among that we have 3 no and 2 yes. Okay, so among that 3 negative and 2 positive. So when on calculating that sunny, it just has an entropy of 0.971. Okay, this subset is fairly mixed, and here the entropy is high also. So splitting here doesn't give us a pure branch. Okay, so let me just go with the next one. And kindly just observe, what is the next one? Yes, it is overcast. So towards overcast, and observe, dear friends, here the overcast, it just has 4 samples, and among that 4, everything are yes. So it just has 4 yes and 0 no. And yeah, kindly just observe, dear friends, towards this, it is a perfectly pure subset and the branch is ideal. No further splittings is needed here when you just choose overcast as your root node. And when on going towards the rain as your subset, again it just has 3 positive and 2 negative, and it also has the same impurity. Now what's next? We have to calculate information gain for all these such a probability. Let's compute the overall information gain of outlook, and outlook with the sunny, overcast, rain as its subset. So what I have to do, here the whole data sets of entropy and subset of sunny, subset of overcast, subset with rain, I have to calculate. And kindly just observe, dear friends, here what we have. So of course, you all know this entropy, yes, we have 0.94, and totally it is 14 samples, and among 14 samples we have 5 for sunny and 4 for overcast and 5 for rain. And here we have to apply this value, that is the value of subset, we have to apply, and we have to calculate the information gain of outlook, and we just got 0.2464. A promising note, yes? Yeah. So here outlook, it just the information gain of outlook, it just gives 0.2464. Next, of course, let me access for temperature, the next one. And here kindly observe, it has further 3 classes: hot, mild and cool. And overall, the subset of this data set, overall the entropy of this whole data set, we have the same. Okay, and furthermore, we are going to have the subset as like hot, mild and cold. And kindly just observe, for hot, we have, this is, yeah, here we have. So hot, of course, we have 2 no and 2 yes. Okay, so a perfect of 50-50 split. And when on just calculating the entropy, it is 1. And towards the subset as like mild, kindly just observe, we have mild as totally 6 samples. And among that 6 samples, we have 4 yes and 2 no. And towards the cool, of course, we have 4 samples. And again, towards the 4 samples, we have 3 positive and 1 negative. Okay. And when on just calculating, kindly just observe, dear friends, here when on just evaluating the information gain of the feature temperature, what we just get is, so here hold on towards temperature, we just get 0.0289, a very small gain, So temperature is not a strong node. Kindly just observe, dear friends, here I just again repeat, for entropy, 0 is purity, 1 is impurity. And towards information gain, whichever it has the highest information gain, that is selected as like a good node, a best node. So here it is very, very small. So we are just keeping it as like a least node. Okay, now let me just move on to the next attribute, humidity. And towards the humidity, yes, kindly just observe, here we have only 2 further classes, high and normal. And among 14 samples, we have 7 high and 7 normal. And of course, among 7 high, we have 3 positive and 4 negative. And among 7 normal, we have 6 positive and 1 negative. And here we just go with the entropy of high and normal. So among 14, 7 high, among 14, 7 normal. And with that, let me just apply the entropy. So when on making this, yes, it is 0.985, almost completely uncertain, a close balance between positive and negative. And here 0.59, of course, most examples are positive. And when on just calculating, putting it all together, and humidity is better than temperature, but still not strong as outlook. Okay, not strong as outlook, because here it is lesser than outlook. Okay, the value of information gain is lesser than outlook. So let me just go with the next attribute, wind. And here, yes, among 14 samples, we have the entropy of the whole. Okay, and now here when on just making it, kindly just observe, it has 2 further classes as like strong and weak. And here, yeah, almost 50-50. Okay, and here we just get entropy 1, which is highly uncertainty. And when coming towards weak class, observe, dear friends, it is 6 positive and 2 negative, and we just get 0.8113. slightly better, but still mixed. Okay, so let me just compute the information gain for wind. And here we have only two classes. So among 14, 6 strong, and among 14 we have 8 weak weak classes, and altogether we have 0.0478. And kindly just see here, dear friends, when on taking it all together, information gain of outlook 0.2464, information gain of temperature, it is 0.0289, and information gain of humidity, it is 0.1516, and for wind it is 0.0478. And here outlook gives the highest gain, so we select outlook as our root node. And when on selecting this outlook as our root node, since it gives us the highest information gain as 0.2464, and now let me just branch the data set based on to the value of outlook. And here, when on having this outlook, I am just going to have only the classes of outlook here. And for sunny, we have 5 samples. For overcast, we have 4 samples. And for rain, we have 5 samples. And kindly just observe, dear friends, when on just applying towards overcast, everything are positive. At most, we just leads towards this positive. Since all samples are positive, entropy would be 0 and no further splitting is needed. So this becomes a leaf node with class yes. And here decision play is equal to yes for overcast. When on just taking sunny as your class, kindly just observe, dear friends, we need here, we took the 5 samples, and in this 5 samples, the sample D1, D2, 8, 9 and 11 would have further recursive to each subset. Yes, we are going to apply again this ID3, and let me just do the subset further. Now, taking it into D1, D2, D8, D9, D11. So on here, when on just calculating the entropy of sunny, okay, if I just calculate entropy of sunny, observe, first of all, sunny, we have 5 these samples, and here this is the possible positive probability and negative probability, and yes, we just have the 0.97 as its entropy. And here, when on considering this temperature as its subset, we have 3 more. We have 3 more classes as like hot, mild and cool. And among this, 2 classes are in hot. Both are having the same resultant. And for cool, it is only 1 sample, and that it also leads with a leaf node yes. But when on just going with mild, yes, it has 1 yes and 1 no. Okay. So with this functionality, so let me just calculate for a subset of hot, we just get resulted with 0 entropy. Subset of cool, it's just 0 entropy. And leading this mild, we just get 1 as our entropy. Now let me just go with this entropy. We would just apply the information gain, and further information gain for this temperature with these classes. So let me just apply information gain for sunny with temperature. And kindly just observe, dear friends, for this temperature we have 3 such classes. So among 5 samples, 2 classes under hot, 2 classes under mild, and 1 classes at cool. And with this, I'm just getting the information gain of sunny towards the temperature. It is 0.57. What's next? Of course, now with this sunny, we have to calculate it for humidity, and with this sunny, we have to calculate it for wind also. So so here we just go with humidity, and for humidity, it just has two further classes, and kindly just observe in that condition for high everything or no, and the humidity normal, yes, both are as yes. Easy, na? So yes, here entropy is 0 for both, and information gain, further calculating the information gain under sunny towards humidity, kindly just observe we have totally 5 samples, and among 5, 3 is high, and among 5, 2 is normal, and its information gain is the one best 0.97. It completely removes uncertainty. It's a perfect gain functionality. Okay, anyhow, let me just go with the wind also. Kindly just observe among sunny, when on calculating towards the wind, two further classes, that is strong and weak. And among 5 samples, yes, 2 samples under strong and 3 samples under weak. And here we have the entropy for strong and entropy calculation for weak. And let me just calculate the information gain for sunny towards wind, and here it is 0.0192. Now, observe dear friends, from sunny, if it is temperature, the information gain is 0.5. From sunny, if it is humidity, yes, it is 0.97. And from sunny, if it is towards wind, it is 0.192. And which has the highest information gain? Yes, it is humidity. And yes, dear friends, with the highest information gain, kindly just see, yes, outlook, if it is sunny towards the humidity, we can easily, where if the humidity is high, yes, you don't play. If it is sunny and towards humidity is normal, yes, you go for play. Yes, dear friends, here we can summarize the sunny branch towards on, splitting towards on humidity. Now, next, outlook towards rain. Let me evaluate this attribute. Okay, so towards this attribute, yes, dear friends, we have these 5 samples. So I just go before again. So D4, D5, D6, D10 and D14. So these 5 samples, and from these 5 samples, we have 3 positive and 2 negative. So whole for that, that is entropy of this outlook towards rain, we have to calculate with this as 3 yes and 2 no. And further we have to calculate it for this temperature class. Further we have to calculate the attribute temperature, and among temperature we have hot, mild and cold. Observe hot, mild and cold as 3 classes. So this is the whole entropy for this data set, and further it is subdivided with hot, mild and cold. Yes, in hot there is no samples, and in mild class of course we have 3 samples, and under cool class we have 2 samples. And observe the exact entropy for this, and once on calculating the entropy, we apply it on to the information gain, and information gain of rain towards temperature, we just get this. What's next? Of course, we have to calculate the same information gain of rain towards humidity, of rain towards wind, and let me just have the humidity. Yes, we have high and normal, and here we have the entropy, and here we get the information gain of rain towards humidity. And the next information gain towards wind, we have two further classes, strong and weak, and both are 0, and towards that we have the highest information gain. And there we go, dear friends. So here from rain towards temperature, we have information gain of 0.01, and from rain towards humidity, it is again 0.01. Rain towards wind, we have the highest information gain, that is 0.97. And kindly observe here, dear friends, under outlook, if it rains and if we have a strong wind, we don't go for play. And under outlook of rain, if we have a weak wind, we go for play. So this is the exact resultant, dear friends. And yes. So here, when on just making towards outlook, if it is overcast, yes, you go for play. On outlook, if it is sunny, and comparing towards that high humidity, you won't go for play, and if it is normal humidity, you go for play. And last but not least, yes, we end up here towards outlook when it rains, and if we have a weak wind, you go for play, and if it is a strong wind, you don't go for play. And there we have it, our final decision built using ID3 algorithm. Dear friends, when it is a continuous data, kindly just have a note. For an example, if we have a future like this and towards the output, for an example, let I have a continuous future value 2.3, 3.6, 4, 5.2, 6.7, 8.9, or 10.5, or 14.2. And here we have the output as like yes, no. Again, let me have yes and no, and yes and no. Okay. How we just do this functionality? Dear friends, when you have a numerical value towards the decision tree, when you just apply a regression concept, the first step is you have to make this future in a sorting order. And the next one, the second step, kindly apply a threshold value, and with that threshold value, identify the exact future where the output is continuous number instead of a category. Okay, so here let me just have a simple numerical example, dear friends. So here I just want to predicting a house price based on a house size using decision tree regression. So we have 7 samples. Okay, and among 7 samples we have 2 future. Okay, one is size and second one is price. So here the size of the house in square feet and the price of the house in thousands of dollars. Now, our objective is to learn a decision that can predict price based on the size. Dear friends, in regression tree, instead of calculating entropy, we look at how much variance or error is reduced after a split. Okay, now we will try it in different split point on the size attribute. Okay, so let me just have any of the thing. So I just go with the 2 of the possibilities. Okay, so one is size that is less than or equal to 1300, and another one a size less than or equal to 1500. Let I just take this. Okay, so at each steps we will compute the mean square error. okay, before and after the split, and choose the one that gives the most error reduction. Okay, so let me just go further. First of all, observe this. I just have a note on towards this 1300, and this is one on side and this is another on side. Okay, fine. Okay, so now let me just split the size that is equal to 1300. Okay, so on this, let I have once again. So here, yeah, on here, this is 1300. So let I just have on left side, I have 300, 330 and 350. And on right side, 30. So on right side, I have 370, 390, 400 and 430. Now, let I calculate the mean value, average, and let me just go with mean square error value. Okay, so here mean value I just get 326, and here it is 326.67, and here it is 397.5, and mean square error here I just get 422.22, and for right side it is 481.25. Now for this, let me just calculate the total mean square error. Okay, so total mean square error, let I just calculate here. Among 7 samples, I have 3 at left side, and its mean square value is 2222, and among 7 I have 4 at right side, and its mean square value it is 481.25, and when on calculating I just get 456.07. Okay, let's compare this with other split also. Okay, now what is the next one? So here size which is equal to 1500. This is what I just took. Okay, let me try a split on here, and here if I just have this as my functionality, what is my right and left? So here this would be my left and this would be my right. Okay, so fine. So yes, dear friends, 300, 330, 350 and 370 comes this side, and here we get 390, 400 and 430. Now what is the mean square error here? On this left side I just get 718.75, and towards right side it is 288.89. And kindly just observe, dear friends, let me just have the weight total mean square error. So among 7 sample I have 4 on left side with 718.75, and among 7 I have 3 on right side with 288.89, and when on just calculating this 538.27. So the split gives us high error than the previous. Yes, so here the error is 456 and here we have 538. Okay, among the two which we have tried the split of size 1300 and 1500, kindly just observe, dear friends, we have the lowest MSE in 1300. So we choose this as our first node in our decision tree. And let's now apply the same process recursively on both the sides. And here, when on taking towards this subset, I have three samples, that is 300, 330 and 350. Let me just split it further by 1200. So in such a case, we have furthermore on left side, I just have 300 and 330, and on my right side, it is 350. So kindly just see here, dear friends, when on taking this as my subset split, I observe the mean value here as 315 on my left side, and my MSE value, it is 225. And towards the right side, the mean value, it is 350, and the MSE here, it is 0. And when on just calculating towards the total mean square error, kindly observe, dear friends, I have totally 3 samples and 2 on my left with 225 as my MSE. Under 3 sample, 1 on my right side with 0 as my MSE. I have 150 as my total MSE. Significant reduction. So we split again at 1200. So this is accepted. So now let we visualize our final regression tree. So 1300, and further if it on left side and here towards the right side. Okay, so here in left we have further a subset of 1200, yes or no. And kindly observe, dear friends, here when on just choosing the mean value, here if it is 1200, if it is yes, yeah, here we have 315, and for no we have the mean value as 350. So now each leaf node outputs, here we just predicted a price, which is just the mean of the price in that group. So if a new house of size of 1250 square feet, I want to predict the price of it. So here kindly just observe the 1250, whether it is lesser than or greater than 1300. Yes, it is less. So it just comes here. And towards it, I have a subset of 1200. And when on comparing towards this, whether the 1250 is less than this subset or not. No, actually it comes here. It is greater. So here, this is the exact predicted value for this new house. And here it is decided as the new house of square feet 1250 is predicted as $350,000. So this is how a decision tree regression learns to predict numerical value using recursive binary split. And yes, dear friends, so let's wrap things with a quick recap. So decision tree are powerful models that split data based on the feature to form a flowchart of decision. And here each split we aim to create pure subset, and we need metrics to measure the purity. Here we just used entropy, which is a measure from information theory. So it quantifies impurity, and lower entropy means more confidence in classification. And next we just gone for information gain. So that tells us how much entropy we reduced after a split. And here the higher the information gain, the better the split. And next we just discussed about Gini impurities, which is a simpler, faster alternative to entropy, but it is widely used in cart-based decision tree. Dear friends, regardless of the metric used, the goal is always the same: to reduce impurity and build a decision tree that generalize well to unseen data. So understanding these metrics is more than just maths. It's understanding how your model thinks. If you can grasp how tree splits based on these concepts, you will well on your way to mastering decision tree algorithm. Okay, dear friends, we explored how tree splits using entropy, information gain, and how the Gini index offers an alternative path. So, and how classification trees guide decision, and while regression trees makes a prediction. So, if this video helped clarify things, hit that like button, share with your friends, and subscribe for more machine learning explainers. If you have questions, I'm always around in the comments. So thanks for watching. See you in the next video, dear friends. Happy learning.